Welcome to this rigorous scientific lecture on radiative cooling coatings. Today we're going to walk through the complete experimental workflow that researchers use to discover and validate these remarkable materials. Before we dive into the methodology, let's understand what passive radiative cooling actually is. Passive radiative cooling is the phenomenon where a surface cools below the ambient air temperature without any energy input, purely through thermal radiation to outer space. This works because Earth's atmosphere has a transparency window between 8 and 13 micrometers wavelength, where infrared radiation can escape directly to space. Here's the energy balance. The coating emits infrared radiation toward cold outer space at 3 Kelvin, while simultaneously reflecting solar radiation and exchanging heat with the ambient air through convection. Step 1 in our workflow is performing detailed spectral measurements. This is the foundation of everything that follows. We need to measure two critical spectral properties, the solar reflectance spectrum and the thermal emissivity spectrum. Solar reflectance covers the wavelength range from 0.3 to 2.5 micrometers, which is where most of the sun's energy arrives at Earth's surface. Thermal emissivity covers 2.5 to 25 micrometers, which is where room temperature objects emit most of their thermal radiation. We use a spectrophotometer equipped with an integrating sphere to measure reflectance across all angles. For emissivity, we use Fourier transform infrared spectroscopy. Here's a typical solar reflectance spectrum. An ideal radiative cooler should have reflectance close to 1 across the entire solar spectrum to minimize absorbed solar energy. Let me ask you a question. Why is high solar reflectance so critical for radiative cooling? The answer is that solar irradiance at Earth's surface is approximately 1,000 watts per square meter. If we absorb even 10% of this, that's 100 watts per square meter of heating we must overcome. The absorbed solar power equals 1 minus the solar reflectance rho times 1,000 watts per square meter. Here's the thermal emissivity spectrum. Notice the highlighted region from 8 to 13 micrometers. This is the atmospheric transparency window, where we want maximum emissivity to radiate heat directly to space. Step 2 is computing the expected net cooling power from our spectral measurements. This is where we apply physics to predict performance. The net cooling power is the difference between the radiation emitted by our coating and the radiation it absorbs from the sun, atmosphere, and surroundings. The cooling power equals radiated power minus absorbed solar power minus absorbed atmospheric radiation minus convective heat transfer. The radiated power follows the Stefan-Boltzmann law integrated over our emissivity spectrum. P rad equals the integral of emissivity epsilon of lambda times the blackbody intensity at temperature T over all wavelengths lambda. The atmospheric radiation depends strongly on atmospheric temperature, humidity, and the angular distribution of sky radiance. P atmospheric equals the integral of emissivity times atmospheric radiance over wavelength and solid angle omega. Let's do a quick back-of-the-envelope calculation to estimate the cooling power of an ideal radiative cooler. Assume we have perfect solar reflectance of 1 and emissivity of 1 in the 8 to 13 micrometer atmospheric window and 0 elsewhere. The atmospheric window covers about 20% of the thermal spectrum, so radiated power is approximately 0.2 times sigma T to the 4th power. At 300 Kelvin, that's 0.2 times 5.67 times 10 to the negative 8 times 300 to the 4th. This gives us approximately 92 watts per square meter of radiated power. The atmosphere radiates back to us roughly 60 to 70 watts per square meter in the window region, depending on humidity. So the net radiative cooling power is approximately 92 minus 65 equals 27 watts per square meter under clear sky conditions. With typical convection coefficients of 3 to 5 watts per square meter Kelvin, this 27 watts per square meter translates to roughly 10 Kelvin of sub-ambient cooling. Step 3 is performing carefully controlled outdoor temperature measurements. This is where theory meets reality. It is absolutely critical to have proper control samples. We need to isolate the effect of our coating from environmental variables. A typical setup includes our test sample and a blackbody control placed side by side under identical conditions. Here's the experimental setup. Both samples sit on insulating foam to minimize conductive losses. Thermocouples embedded in each sample continuously record temperature. We simultaneously measure sample temperatures, incident solar flux with a pyranometer, wind speed with an anemometer, and relative humidity. Tests should run for at least 24 hours to capture full diurnal cycles, and ideally several days to assess repeatability and capture varying weather conditions. If our coating works, we expect the test sample to remain several degrees cooler than the blackbody control, especially during nighttime when solar heating is absent. Here's typical data. The yellow line shows ambient air temperature. The red line is the black control, which gets very hot during the day. The green line is our test coating, which stays much cooler and even drops below ambient at night. Here's an important question. Why doesn't the blackbody control cool below ambient temperature at night? The answer is that a blackbody has emissivity of 1 at all wavelengths, so it emits strongly but also absorbs all the atmospheric radiation. The net radiative exchange is nearly zero. Our selective coating is clever. It has high emissivity in the atmospheric window where the sky is cold, but low emissivity elsewhere where the atmosphere radiates back strongly. Step 4 is developing a comprehensive heat transfer model and using our experimental data to fit unknown parameters, like the convection coefficient. Our model must include all modes of heat transfer: radiation to sky, radiation from atmosphere, solar absorption, convection to air, and conduction to substrate. The thermal mass M times specific heat Cp times temperature change rate equals net radiation minus convection, where H is the convection coefficient and T ambient is air temperature. The convection coefficient H depends on wind speed and typically ranges from 5 watts per square meter Kelvin in still air to 15 in moderate wind. We determine H by running our model forward in time and adjusting H to minimize the root mean square error between predicted and measured temperatures. H equals the argument that minimizes the square root of 1 over n times the sum of T model minus T experimental squared. Once we fit H for multiple wind conditions, we can develop an empirical correlation showing how H increases with wind speed. A typical correlation is H equals H0 plus K times wind speed to the 0.8 power, where H0 is the natural convection coefficient. A good model will accurately reproduce both daytime temperatures when solar heating dominates and nighttime temperatures when radiative cooling dominates. Step 5 is the ultimate test: validating our model by predicting cooling performance under different atmospheric conditions that we didn't use for fitting. The key environmental variables that affect radiative cooling are atmospheric humidity, cloud cover, and ambient temperature. High humidity increases atmospheric radiation in the 8 to 13 micrometer window because water vapor is a strong absorber and emitter in this range. We can model atmospheric power as a function of relative humidity. P atmospheric at RH equals P atmospheric dry plus alpha times relative humidity. Clouds are nearly opaque in the infrared and radiate at approximately ambient temperature, so they essentially eliminate radiative cooling entirely. A strong validation test is to compare model predictions against measurements on a humid day versus a dry, clear day, using the same fitted convection coefficient. Here's a validation plot showing cooling power versus humidity. The green dots are measurements, and the blue line is our model prediction. Good agreement validates our physical understanding. For even more accuracy, advanced models consider that sky temperature varies with zenith angle, because you're looking through different atmospheric path lengths. Sky temperature, as a function of zenith angle theta, approximately equals ambient temperature minus delta T divided by cosine theta. This angular dependence affects the integral over solid angle when computing total atmospheric radiation incident on our surface. Let's work through a practical example. Designing a radiative cooling coating for a hot arid climate like Phoenix, Arizona. Our design goal is to keep a surface at 25 degrees Celsius when the ambient air temperature is 40 degrees Celsius. That's a temperature difference of 40 minus 25 equals 15 Kelvin below ambient. Assuming a convection coefficient of 8 watts per square meter Kelvin in typical desert wind conditions, the required cooling power is H times delta T equals 8 times 15 equals 120 watts per square meter. This is extremely challenging, because 120 watts per square meter exceeds what typical radiative cooling can achieve, especially during the day with solar loading. The solution is to combine radiative cooling with aggressive solar shading or near-perfect solar reflectance above 98%. But here's an interesting question. What if we only need cooling at night, when solar load is zero? Then it becomes much more achievable because we can access 50 to 100 watts per square meter of net radiative cooling without fighting solar heating. Let's briefly discuss the material science behind these coatings. What materials actually achieve the required spectral properties? High solar reflectance is achieved using white pigments like titanium dioxide or barium sulfate particles that scatter all visible and near-infrared light. The polymer matrix must be transparent in the mid-infrared. Common choices are polydimethylsiloxane or polymethylpentene. Thermal emissivity is enhanced by polar chemical groups in the polymer or by incorporating ultra-thin metal films with carefully designed thickness. A real high-performance coating uses silica microspheres embedded in PDMS. The microspheres provide solar scattering, while PDMS provides infrared emissivity. Such coatings achieve solar reflectance greater than 0.96 and emissivity in the atmospheric window greater than 0.93. Let's summarize the complete scientific workflow we've covered for discovering and validating radiative cooling coatings. Step 1. Perform careful spectral measurements of both solar reflectance and thermal emissivity across the full wavelength range. Step 2. Use these spectra with fundamental radiative transfer equations to compute the expected net cooling power. Step 3. Perform rigorous outdoor temperature measurements with proper control samples and comprehensive environmental monitoring. Step 4. Develop a complete heat transfer model and fit it to experimental data to determine convection coefficients and validate the energy balance. Step 5. Validate the model by predicting cooling performance under different humidity, cloud cover, and wind conditions that weren't used in the fitting process. This systematic methodology ensures scientific rigor, allows for reproducibility by other researchers, and provides confidence in the claimed performance. Let me leave you with some key insights and design principles that emerge from this analysis. First, solar reflectance is just as critical as thermal emissivity. Even a small amount of absorbed solar radiation can completely negate radiative cooling. Second, convection becomes the dominant loss mechanism whenever wind is present, which is why radiative cooling works best on calm, clear nights. Third, atmospheric humidity has a profound effect on cooling power because water vapor increases atmospheric radiation in the transparency window. Fourth, spectral selectivity is crucial. Average emissivity is not enough. You need high emissivity specifically in the 8 to 13 micrometer window. What performance can state-of-the-art radiative cooling coatings actually achieve in practice? At nighttime, under clear, dry skies with low wind, the best coatings achieve 5 to 10 Kelvin below ambient temperature. During daytime, under direct sunlight, they can achieve 1 to 3 Kelvin below ambient, which is quite remarkable given the intense solar heating. In terms of cooling power, nighttime performance typically ranges from 40 to 80 watts per square meter, depending on atmospheric conditions. Practical applications include supplemental building cooling, enabling passive water harvesting from dew, and preventing sensor overheating in remote locations. Finally, let me highlight some exciting future directions and open questions in this field. Can we design coatings that work effectively in humid tropical climates where atmospheric radiation is very high? This remains a significant challenge. Can we develop coatings that maintain their performance for decades outdoors while remaining self-cleaning and resistant to degradation? Can we scale up manufacturing to produce these coatings at costs comparable to conventional paint, perhaps under $1 per square meter? Can we intelligently integrate radiative cooling with photovoltaics for simultaneous power generation and cooling, or with phase change materials for thermal energy storage? In conclusion, discovering and validating radiative cooling coatings is a rigorous experimental science that requires careful spectroscopy, outdoor testing, heat transfer modeling, and systematic validation. Success requires both excellent materials with the right spectral properties and excellent experimental methodology to accurately characterize performance. This field beautifully combines concepts from optics, thermodynamics, atmospheric science, and materials engineering. By following the systematic workflow we've outlined today, researchers can produce reproducible, scientifically sound results that advance this exciting technology toward real-world deployment.